everyone. Thank you all very much for coming. My name is Doug Hawkins. I am a lead JIT developer at Azul Systems. We make a Java virtual machine called Zing, aimed at high performance, as well as an OpenJDK distribution called Zulu that you may have heard of. And a lot of my job actually ends up being just digging into weird performance anomalies. And this is sort of me showing you what I do when I want to understand these things. Now, obviously, since I work on a VM and I've done this for 5 years, I think JVMs are pretty fascinating. But I also feel the details can be a bit abstract and can feel a bit far removed from what you're doing every day. And on some level, that's good. You shouldn't have to know. That's kind of my job. But when things go wrong, it is good to have a little better idea what's happening under the hood. And that can be difficult because the JVM is honestly an amazing piece of technology. It's also an amazingly complicated piece of technology. It has dynamic instrumentation and profiling, and it's doing just-in-time compilation and a garbage collector and all these moving parts that are constantly trying to adapt to your application. As one of my colleagues who used to work at Sun in the early days put it, it's alive. It's constantly trying to react to your program. And that can be really hard to understand. And much of my job is investigating the performance anomalies that come out of these problems. Basically, I spend inordinate amounts of time staring at log files, which isn't always the most fun thing in the world, to be honest. But it is important when you're dealing with big, high-performance applications. And I'll give a lot of credit to Brendan and Greg for sort of popularizing the idea that we should use visualizations to understand what's going on. Brendan and Greg is the performance architect at Netflix. He deals with things on a ridiculous scale, and he has popularized this idea of flame graphs as a nice way to look at where the hot points are in our code. And it's not that we didn't have tools to visualize hot points in our code before. We did. But the right visual can make a huge difference when you're dealing with millions of lines of log or tens of millions of lines of log, because you just can't read all that. So today we're going to use some tools, some that are free and some that I've sort of hacked together myself in the course of my job to just see a little bit of what's going on inside of the VM. And as usual, I'm going to start small. I start with a very simple program where it's easy to see the performance characteristics of the program. So this is pretty much the whole program. I've got a main. The core part is that blue line in the middle. We're just summing up a bunch of numbers, in this case, 20,000 numbers. I just produce those randomly, and I measure how long this takes in this outer loop. To make sure that the VM doesn't get too clever, I have to store that result of sum into a public variable so that it doesn't get smart and optimize that away. And I also mutate the array a little bit every time through the loop, because otherwise it might say, store the result from the first iteration of the loop and never recompute again. Perfectly valid optimizations, and if you're not really careful, those sorts of things can happen and you're not measuring what you think you're measuring. But that's the gist of the program. Sum up 20,000 numbers, see how long it takes, do that 200 times. And just to make sure that I'm not perturbing things, I create a side structure to store the iteration results ahead of time. I just update it, and I don't print out the results until the end. I don't want any I/O interleaving with my summation operations. And I'll just run that program. It's here. We'll max it. And we'll run it with JDK 8. And just to make sure no GC is happening, I also turned on print GC details, just so we don't see any GCs interleaving with the output or the measurement phase, which is actually at the top before the table. And this is what I get. Now, I did actually make it slightly more complicated than it indicated. I actually measure sub-millisecond time by using some complications of current time millis and nanotime, but you get the basic idea. So get this table, and at the very beginning, we're running in the interpreter. I think you all know that. And our iterations aren't terribly fast, a few 100,000 nanoseconds to sum up these numbers. And then, since we're using Java 7 or later, we now have tiered compilation on by default. And we're going to go to a tier 1, a baseline JIT, C1, and things will get a bit faster. We get to about 50,000 nanoseconds, so we've improved by almost an order of magnitude. And then as we keep going, we'll get to the second tier JIT, C2, and we'll get to around 7,000 nanoseconds. So we've improved by almost 2 orders of magnitude. And this is the process your program is going through. This is for an individual method, so it's really simple. It's basically just the summation method that we're interested in. And if we plot it, we get a graph like this. This is on a log scale. Y-axis is durations, x-axis is iterations. And we can see the 3 distinct phases. Interpreter, then baseline JIT, C1, then optimized JIT, C2. But I think we're already not off to a great start here. If you think about that x-axis as time, you got it wrong. Because each iteration is not the same length, right? The interpreter is slower than C1 is slower than C2. So let's plot it in terms of time. And here I've marked every 10 iterations with this vertical hash that's dashed. And you can see a little better what's happening. Now you might think I'm cheating by using time on the x and y axis. That might be fair, but at least now we can actually kind of see what's occurring. The first 10 iterations take about 3¼ milliseconds. The interpreter's not super fast. Then C1 kicks in, and we do about 50 iterations in about 3½ milliseconds. And then at the very end, we do the last 80 iterations in about ½ millisecond. But what happened between 60 and 70? My goodness. There's actually a single iteration that takes as much as 20,000 to 3 million nanoseconds, I think because of switching costs between C1 and C2. You couldn't really see that in the previous graph, could you? No. So the way we look at the data does actually make a big difference. And there's actually more to tiered compilation than just C1 and C2. The basic flow we're going through right now is the normal flow. We start off in the interpreter. We go to C1 in what's called tier 3, where it's doing instrumentation, which feeds extra information to C2 so it can do cool speculative optimizations. That's the normal flow, but there are a couple other flows, and we'll come back to those a little bit later. And you could see this if you wanted to. If you've watched any of my prior talks, you'd see, okay, I could turn on print compilation, and I can see some of this happening. In blue here, I can see some being compiled at tier 3, both a loop compilation, which has that at 14 out to the side to tell me where the loop is, and the full method, which doesn't have the at 14. And then I see the tier 4 happen. That's also a loop compilation. And when the tier 4 gets created, the VM will actually discard the tier 3, and that's why we see the tier 3 being made not entrant. And then later on, we see the full compilation at tier 4. That's when we reach our peak performance. But it's a little hard to see all of this relative to our performance, and these logs get large, really, really large. Most real programs will have at least a few thousand JIT compilations. And of those, maybe 10 to 50 will actually matter to the performance of your application. So you've got to find them if you actually care about the performance. That's a bit of a challenge. And there's actually hundreds of deoptimizations as well. We'll throw away compilations, not just because we're moving to a higher tier, but because we made some speculation and it didn't work out. And again, the only ones that matter are the ones that affect your hot methods. So it's like one deoptimization out of hundreds might be important. Now, there is a tool that I very much like for just poking around called JVM that will let you do some of this. So I'll use JVM with the program we just ran. I have JVM here. Apologize that the font is not bigger. Let's take it off. And with JVM, you can open a log. I produced this log as I was doing the run earlier. And you give it this XML file that the VM produces that contains all sorts of stuff. Then you tell it to start processing the log. And we can produce a nice visual timeline of the compilation activity. Okay, that's pretty nice. And at the top, it actually tells me there are 198 total compilations. That's pretty small because this is a small program. 175 of those were C1. 15 of those were C2. 2 of those were OSRs. All right, that's something, but I really don't know how that related to the performance of my program. But I think this is a good start. And it's certainly better than reading that XML file. The way you get that XML file is to run with this. And it's pretty awful, if I'm being honest. I've written a parser for it. It wasn't fun. But it's very rich in information. And you can use JVM to see that XML snippet just as it pertains to your method. I can go into JVM. I can go back to the methods view, find my sample program, go into here, show the try view. It's open in the background, I think. Yeah. And go to journal, and it'll show me just the part of the file that pertains to my method. This, of course, presumes I know which method I should be looking at, but I do have these tools. And I think JVM is absolutely wonderful for writing toy programs and poking around. It will give you a triple view of your Java source code next to the bytecode, next to the machine code, if you get it all set up properly. And I've done a video series about using JVM. The guy who created it has done a better video series about it, Chris Newland. It's absolutely worth your time to go check it out. There are other tools. There's Mission Control, which Oracle has recently open sourced, and it will give you a similar view. You can go into code, compiled methods after you've done a recording, and you can see this graph over time. It's showing it in terms of bytes of code produced, but it's largely the same picture. But as I said, I want to know more. I want to know how this relates to the performance of this simple program. So I plotted this same line against our simple program's performance. Yep. Getting a bit ahead of myself. And I also want to know this exact tier breakdown as well. Like, I don't want to just know C1 and C2 because there are these other behaviors. There's tier 1, tier 2, and tier 3, and they're for different things. I would like to see those too. So the first thing I do, and this is actually something JVM will give you as well, you can get tables of breakdowns by compilation type, but I wanted to break down by tier. And so I have an API that I like to use that just lets me query files. I just say, read in this log file, same file that JVM used, select all the compiles, do a mapping by tier, so I now have a stream of tier numbers, and process that with a counter, which just makes this table. And I think this is a really powerful way to explore what's happening. So here's that program. Right now I'm going to do by tier. And there you go. 136 tier 3s, 38 tier 1s, 15 tier 4s, 1 tier 2. Now I can get a little more resolution to my data. And if I want to break it down by tier and OSR, well, I could do that too. There we go. It's not the prettiest format I'll give you, but it's a pretty quick way to get answers to questions. And this is really useful in my day-to-day work of just trying to figure out what's going on in somebody's application who just had a performance problem, because I really don't know what I'm looking for. I'm starting with a guess, and a canned visualization might give me what I want, and that's an excellent place to start, but it has its limits. And then I can, of course, take this and plot compilations over time by tier. And I think this is pretty interesting because one of the cool parts about Java's tiering system is it does have these different modes. It has tier 1 compiles, which are only used for trivial methods. And we expect most trivial methods will be identified pretty early. We'll load the class. We'll try to get something, we'll find out that method's trivial, and we'll tier 1 compile it almost immediately. And we can see that's pretty much the case. Looking at this graph, which is in terms of time, we can see almost all of the tier 1, which is in green, is discovered at the very beginning, and then we discover a little more at the end. This is a slightly different benchmark because I wanted something bigger, but you get the idea. Tier 2 is actually pretty much only used during phase transitions in the application. At the beginning, when tier 4's queue gets backed up, that's when we use tier 2. Most of the time we go straight to tier 3, we skip tier 2, but if tier 4 is too busy, we'll go 2, then 3, then 4. And we can see that happening. The yellow peaks at the beginning, and then we get rid of some of the tier 2s, move them to 3, and then we move the 3s to 4, and we can see that happening in this graph. And we can actually even see the 4s gradually replacing the 3s. So here the numbers actually go down as we make the tier 3s and tier 2s not entrant, and they get replaced by a higher tier. So you can see the red line getting thicker over time. And at the very end, the application switches its behavior, and we do some more compilation, and we can see that too. But where I think it really starts to get fun is breaking things down by package. I can actually just write a program like this, find all the compiles, map them by the package name, and count them. And that's for the simple program earlier. There were 30 compilations of Java Lang. That kind of makes sense. I think all of you end up using Java Lang. Java util regex, I honestly don't know. I'm outputting some stuff to a file, and I'm using formatting to output to the console. I guess maybe that uses something from the regex package. That's kind of interesting. I'd like to investigate that. Java util, okay, collections. Everybody uses collections. Java NIO, Java IO, yeah, that's for outputting the table at the end. But only 4 of the compiles are actually for our example. Only 4 of those are actually the hot code out of nearly 200. So you've got to find that 1 in 50 that matters. So now let's try to see if it actually did affect the performance of our application. Let's do what I said I was going to do earlier. Let's put our performance graph next to our compilation graph. See how helpful that is. That is the lining of the performance graph up against the compile graph by time. That tiny little blue squiggle at the top is the actual run of our program as we saw it. We really are looking for like a needle in a haystack here. in terms of which compilation mattered. And in fact, the flattest period in our graph is the point where our program is running, because that's when we're kind of doing one thing and we're not compiling new code. But this graph did tell us something interesting. It told us that our application has multiple phases. Our application has to first start up the VM. Not really a surprise. I anchored everything in time relative to the first measurement point. So there were actually 30 milliseconds before that where we were jitting code, and there was actually another 90 milliseconds before that before we were just starting the VM. But we were compiling some stuff. We were, loading classes from the bootstrap, like string and security manager and things like that. You actually load about 50 classes before you even start running main. And some of that gets jitted. And then, after we finish running our benchmark, we're printing out our results. That's when all our I/O is happening. And I'm also writing out a CSV so I can make these pretty graphs. So we're doing extra work. We're writing out results. We're running new code to print out the table that you saw, as well as write out the CSV file. And that was the same thing that was happening with the benchmark you saw earlier on the tiering graph. It was generating graphs and tables and so forth to give you the results of the benchmark. And this isn't really atypical. A lot of our programs go through this. Start up a Cassandra node, and it might read a bunch of data in. And then you switch to querying it, and then you shut it down. Right? You're going to have multiple phases. It's pretty normal. At the very least, you're going to have the VM starting up phase, and then the running phase. Even in something really small like a function as a service or a microservice, you're probably going to have that sort of phase. So we can see that most of these JIT compilations, they're just not important to performance. And of course, we all knew this. Or at least I hope you knew this. This is just the classic Knuth quote. We should forget about the small efficiencies. Say 97% of the time, premature optimization is the root of all evil, yet we should not pass up the opportunities in that critical 3%. You might have heard you spend 90% of the time and 10% of your code. Lie. That is overstating things by at least a factor of 3 or 4. It's like 2 or 3% of your code. It's vanishingly small. You've got to find that if you want to know what's really affecting performance. Now for this, I'm going to do something we usually should not do. I'm just going to guess. I'm going to guess that sum is important to the performance of our benchmark. I know I'm going out on a limb here, but that's what I'm going to do. I'm just going to mark those compilations. Now, hopefully we find that those compilations overlap the running of our benchmark, or something is really, really wrong here. Okay, that's where they occur. That first green line is where both of the tier 3, the C1 compilations happen, both the full compilation and the compilation of the loop. And yes, that is about where we transition into the slightly faster performance. That second green line is where we do a loop compilation for tier 4, C2. And that's right before we see that weird performance anomaly. Can't say that that's definitely the problem, but maybe. And then at tier 4, at the last green line, we have the tier 4 C2 compilation, and that is right before we drop into our best performance. That's what we'd like to see. So this all sort of makes sense. Placing these lines is a little fuzzy, to be honest. Measuring at sub-millisecond timeframes is tricky, but it does actually work out quite closely. And I've run this thing like 50 times, so. Now you can do this with JITwatch as well. I can go and pick my method, and then I can go into the timeline view, and it'll highlight where the compilation got queued and installed, but unless I know that method's hot and I can match it up against my performance graph, it's still kind of limited in how far I can take this. But at least there are timestamps, and I can start to figure these things out. So I've asserted that everything is multi-phase, so can we actually see the phases? That would be cool. I think we can. If we look at compilations by package over time. Something like this. Now it's a little small, so I'm just going to switch to it in a browser. This. So this is a heat map of the program running. Make it a little bigger. And it's composed of 3 colors. The blue is our C1 compilations. The green is our C2 compilations. I didn't break them down by tier. And if we throw any compilations, tier 2 compilations away, there'll be some red. This program doesn't have any red. And then the rows are our packages. So I've highlighted the example package. That's the benchmark we're actually running. And then the columns are buckets in time. In this case, I did 5 millisecond buckets in time, and I count the compilations within them. And at the very beginning, we can see, yep, we're compiling Java Lang and Java Util. We're just kind of getting the VM warmed up. And then, in this run, about 120 milliseconds into it, we started actually compiling our code, the benchmark code. And we did some C1 compilations during the 125 millisecond bucket. That's both the full compilation and the loop. And then we did the loop compilation, and then we did the full compilation, and that's where we reached peak performance. And we can see that, sort of. And then later on, we start writing out our table of results, and these bottom 2 rows are NIO and regex. And right now it's filtering only to show columns that had C2 compilations. There is a bit more going on here. But we can see that there's a whole bunch of stuff we didn't even bother to compile because it just wasn't hot at all until after we finished running the benchmark. And it would be very hard to see that unless you have this multi-dimensional view. So let's add some deoptimization into the picture. I'm going to do it in a somewhat brute force fashion. We're going to run a simple program that I like to call uninitialized forever. This is a program. I have a main. It's going to try to instantiate an object 25 million times. I said try. And the class it's going to try to instantiate, it has a problem in its static initializer. You might see the problem. It always throws a runtime exception. You can never instantiate this class, which means you can never create an instance of this class. Sorry. Right now we have a compilation error in our static initializer. Let me fix that. There we go. That's better. All right. And we're going to run this program, and we're going to see what happens. I wanted to make sure my program was stable. You know, I'm a good Java programmer, so I caught throwable so that it keeps running. Okay, so what do you think happens? We're running a hot loop. What does Hotspot want to do when it sees a hot loop? It wants to JIT it. But Hotspot doesn't like uninitialized classes. So it's going to see that, and it's going to throw us back to the interpreter. But then the loop is still hot, so it wants to compile that. But it doesn't like uninitialized classes, so it goes back to the interpreter. But the loop is still hot. You see how this is going to go. So we're going to run it. There you go. Yeah, this is not a happy system. And I'm just going to leave it running in the background. Now, if we went and looked at this compilation timeline GentWatch, we might get a sense that something's wrong because the graph kind of keeps doing the same thing. It keeps going up a little bit and up a little bit and up a little bit. And really, we kind of expect it to flatten off if this is a long-running program. But it didn't. Well, eventually it does. Okay. I could also go into JITwatch's top lists, and I could look and see uninitialized forever main has deoptimized in a shorter run 7 times. And maybe that means something, but lots of things deoptimize at least a few times. And if this isn't a hot method, that's not necessarily a problem. Or I could go into Oracle Mission Control, and if I go to the Code Errors tab, I could see that I did have a whole bunch of no-class def found errors. I hope that that's a bad sign to you, but I've actually seen this happen in real programs 3 times in the last 5 years. It does happen. Now, eventually it stops. After about 90 seconds. Let's see if it's been about 90 seconds. Yes, it has stopped. Why did it stop? Well, fortunately the VM does have some safeguards. There are some safeguards that if something just goes horribly wrong, and we compile the same thing more than like 40 times, we'll stop doing that. We clearly made a mistake. It is also good at stopping evil people, like me, from doing horrible things to your VM. Of course, I would like to look at these things a little deeper, so I take out my trusty querying API, I query my log, I know what I'm looking for. I'm looking for uncommon traps, and I just make a table by pair and reason, and I find out that main did this 7 times because the class was uninitialized, and that's actually not a bad place to start doing this sort of exploration. It's just the start of the exploration, but it's a start. The heat map can make it a little more clear. We can at least see that the corrective mechanism actually did its job. So here is a heat map for uninitialized. Just 2 packages, Java lang and the example. And we can see that like every 400 milliseconds, because I'm using 200 millisecond time buckets, there's a C1 compile, a C2 compile, a deopt, a C1 compile, a C2 compile, a deopt, a C1 compile. You get the idea. And it just kind of goes like this. Here there were probably 2. And yeah, this is not a healthy system. The rainbow colors are really pretty, but you want to see this stop at some point. Otherwise, the system didn't stabilize. And then, indeed, way out here at around 90 seconds, it does, in fact, stop. I guess we'll call this healthy, but you know, the fact that we did this for 90 seconds is actually indicative of a problem. And just in case you think that these deoptimization things don't actually really matter, they do if you start caring about small enough points in time. I am often working with low latency customers, banks, exchanges, etc. They consider like a couple hundred milliseconds might be considered an outage by some of them if the system doesn't respond. So I plotted a benchmark, and I did a heat map just by compiler and not entrant, and you can see one very noticeable dip. That's a 20% drop in performance caused by a single deoptimization. Just had to hit the right method. This one was the one that was actually running the benchmark. Surprise, surprise, that negatively impacts the benchmark. But it was just one. There were actually a few hundred deoptimizations in this run, but it was only that one that mattered. And this sort of visualization and putting things side by side, I think, can help us understand these sorts of behaviors, which are really hard to understand otherwise. But you got to have, very precise timing information to line all this up. Now, the reason this slows down is because when we hit a deoptimization, we discard the tier 2 compile. In our case, we'll at least go back to C1. In OpenJDK's case, you're going back to the interpreter. I believe Graal will actually let you go back to the middle if you're using the AOT tiered mode. But even so, that lower tier, whether it's C1 or the interpreter, it's slower than the higher tier. And that will show up in your performance if you're looking for it. It might only be a moment. It might only be a few hundred milliseconds. I've seen one that was actually a full second. But it is there. Take one more example view of this. We'll take a bigger benchmark, which has more distinct phases to it, and look at it. So here we go. This is the benchmark. Java Lang, Java Util, the usual culprits. This is going to be true of pretty much all your applications. And if you're running Scala, there's going to be the core Scala library. If you're running Clojure, there's going to be the core Clojure library in addition to this. There are certain things that are just used by every part of the program, but it's slightly different parts of that package, and they just kind of show up as cosmic background radiation in this sort of view. The line I've highlighted here is the actual Xerxes packages. I've folded a bunch of them together because they're like 10 internal packages to Xerxes, but this is an XML benchmark, so it makes sense that that's the code. And you can see it goes through some churn of C1 compiles, C2 compiles, deoptimization, C1 compiles, C2 compiles, deoptimization, before things finally start to settle down out here after about 20 seconds. And then, much like my simple program, this benchmark harness does write out charts at the very end. I did a 5-minute run. And there you go. At the very end, it ends up using a lot more of Java Util, Java Collections, Java Lang, but it also uses some packages it's never used before. In this case, this one draws charts, so it uses org jfreechart. And we can see these phases happening in a way that we just couldn't before. Now, this does mean that you need to think about, if you care about warm-up isn't a single moment in time. Warm-up is each phase of your application. Every time you load some new code, that's going to get JITted. It's not just that you're warmed up. That's not what happens. New code, new phase, new JIT cycle, new warm-up cycle. You also need to think about that warm-up isn't necessarily something you can distill down to a single statistic. One of the things I work on is something that tries to remove a lot of the warm-up by doing the work ahead of time and loading cached code from disk and lots of other things. And that's the green line here, and the blue line is our VM running without that. And if we were just going by warm-up time, they look like, well, they reach their peak at the same point, or their minimum at the same point, since this graph goes down. But I think we could agree that the green line is better than the blue line. Even though the time to warm up, if you're just talking about that statistic, looks kind of the same. And of course, when I did this, I made the same sorts of pretty plots. With the blue line, you can see our system is doing lots of compilations shown on the top. We've got a lot of C1s happening as new code is discovered. We've got a lot of C2, or in our case, we have another JIT called Falcon. And that's happening as the benchmark is getting warmed up. And we're seeing a lot of the orange. We're seeing a lot of deoptimization occurring. And then when I add the technology I was talking about, this changes. We do a lot of compilations up front. So we do thousands of C1s up front and even hundreds of tier 2 compiles before we even start running main. And that's how we get this better warm-up curve. And then the other thing you have to keep in mind is each of these phases is going to have different hot methods. You can't just take a profiler and say, I found the one hot method. If you've got a multi-phase application, you need to profile each of those phases. And most of us do. There are plenty of great profiling tools. I decided not to talk about profiling tools today because I think there are a lot of excellent talks out there already. But you can use mission control and have the table view, and in this XML benchmark I was talking about, it tells me that XML schema validator handles start element as the hot method. Not really a surprise, but it's always good to check. I tried to profile that last phrase with org.jfreechart, and unfortunately, the VM kept shutting down before I could get a full recording, so I eventually kind of gave up. But one nice thing about mission control is it will let you narrow in on a period of time by taking that slide graph at the top and narrowing the time window. So that's pretty cool. And of course, my favorite view is flame graphs, and you can find all sorts of things that have been hooked up to flame graphs. Netflix uses perf. There are people who've used the data from Flight Recorder, which is what mission control consumes to create flame graphs. You can find things that use the sampling profiling built into the VM to produce flame graphs. There are lots of wonderful tools for producing this visualization. So I would encourage you to check those out, but I feel like that's been covered. I did want to cover at least one program that's not completely a benchmark. So I decided I'd try Spring Boot. I just took Spring Boot. I mean, Spring Boot's supposed to be light. And I started it. I didn't really configure much in it. And I just want to see how much JIT compilation it does. So I produced that same XML file and used that to produce a heat map. I was really pleasantly surprised in some respects. Now, there are a lot of packages, and I didn't work so hard to fold them this time. But you can see it actually does no tier 2 compilation. It actually has a very light startup. It just runs a little bit of stuff, does some wiring, and we're good to go. Not a lot happening. But that's kind of a good thing and a bad thing. Because that means you've got a server, it's up and running. Is it warmed up? No. Definitely not. When will it be warmed up? I don't know. When are you going to send traffic to it? It's not just warmed up because you started it. That's not how it works. It warms up in response to some stimulus. We start running methods when we start sending it requests. When we run methods is when we increase counters, which is what triggers the JIT. So just starting it doesn't do much. If the load shows up immediately, great, it'll warm up quickly. If it doesn't show up for a while, it'll warm up later. So I just let it sit there for like 40 seconds. And then I started refreshing the page. And then I can start to see the compilation activity kick in. I was just refreshing this manually. I didn't use a machine. And so we see it's still sort of just like lukewarm. If I really started to hammer it with something like Gatling or JMeter, then I'd see it get hot. But it actually doesn't get hot until somebody starts to stimulate this thing. And for my customers, that's a real problem because they're messaging applications and they want them to turn the server on, peak performance right away, which is why we have this whole sort of pre-warm the VM based off a recording from yesterday. So warm up isn't just, one moment in time we start the VM. It's not one moment in time there's a single phase. Our applications are multi-phase. It depends on how much traffic we're getting. We have to keep that all in mind as we're now doing these smaller deployments. So I just want you to think about that. Now, back to our anomaly from the beginning. What did cause that weirdly long iteration? I honestly don't know for OpenJDK. What I do know is that a couple years ago, I noticed a similar anomaly in our own VM, and it was from switching from C1 to a C2 loop compilation. And I went and fixed that. And part of how I went and fixed that was by doing some visuals, processing, tracing, and looking for these sorts of anomalies. I know that's not what you guys are going to do, and that's okay. I just want you to have a little bit better idea what's going on inside the VM, and maybe give you some ideas on how to go look, hopefully with the off-the-shelf tools, but just so you know what's happening. There are a lot of great tools. I've stuck to showing you the free tools today because I want to give you things that you can go and look at, but there are plenty of wonderful commercial tools, YourKit, Dynatrace. I'm not entirely familiar with all of the capabilities, but I would encourage you to go explore the tools so you can better understand the performance of your applications. I think using visualizations can be very powerful because these logs are gigantic. Even for tiny programs, I'm just looking through like 1 million lines of log file. Does anyone want to look at 1 million lines of log file? No. So we're trying to find these tiny events that are like 3% of the time among these giant files, and I think we need something to help us do that. And so for that reason, I'm actually kind of happy to announce that Azul has given me the go-ahead to open source some of what you've seen today. They're a little rough around the edges. They're not out in public yet, but we are going to put them out there. I'd like the community to play with them. Just see what you think, maybe add to them. Maybe in another couple years, we'll have something even better to play with. All right. Well, that's all I have for you today. I'd like to thank you all very much for coming. If you'd like to learn more about some of these tools, I'd encourage that. Go watch Chris Newland's videos on JitWatch. He also has a new book that he did with a couple others on Java performance for O'Reilly that just came out. I haven't read it yet, but I'm sure it's absolutely worth reading. If you'd like to know more about mission control, there's a YouTube video. It tends to be a little WebLogic focused in their videos, but it's definitely a good tool and has lots of capabilities. Azul has a GitHub. That's for our OpenJDK distribution. We've also contributed things like JHiccup and HDR histogram, which are low latency measuring tools, to the community, and some of those have been used by Netflix and things like Hystrix. So you may already be using some of our open source stuff. And basically, just go read anything that Brendan Gregg has ever written. He is absolutely the expert on this sort of stuff. He does not just Java performance, but Node performance and Linux performance, down to like I/O level of Linux, all sorts of things, syscalls, you name it. Absolutely a wonderful resource. So I hope that was enough to whet your appetite, and thank you all very much for coming.